just like our own, the Soviet robotic and Lunar and Planetary exploration program grew out of the Cold War. It was enabled, of course, by essentially ICBMs. And unlike ours, however, it nearly died with it at the fall of the Soviet Union. And it provided all along during that history kind of a mysterious and sinister stimulus to American efforts on this side, because for the most part we didn't know what they were doing. And they had a habit early in the days of beating us to places. And so it really kind of booted us in the rear end to make sure that we did everything we could to get on top of it. And the reason for this, of course, was most events in this program were unknown and hidden in a veil of secrecy until about the mid-1980s. And most of the events, in fact, are virtually unknown outside of a very closed circle in Soviet secrecy. And all that's really a shame because, in fact, this is a tale of a lot of adventure, excitement, a lot of suspense in this mission, a lot of tragedy. It's a very human story of courage by a lot of people, patience to overcome obstacles that we never heard of, and a lot of failures, in fact. But in spite of all that, it's also a tale of fantastic accomplishment as well as debilitating loss. And the Russian people didn't get to live this. We can only hear about it after the fact. The whole program in the Soviet Union was driven by a thirst for technical achievement and for a desire for international recognition and respect. Back in the late 50s and 60s, and in that sense was actually a success because, in fact, for robotic missions, the Russians were the first on the moon. They were actually the first on Venus, and less well known, they were actually the first on Mars. Now, the early years of space exploration were driven by strong personalities, both here and in the Soviet Union. Men who were visionaries, they were superb engineers, and they were strong leaders. They all came out of the war. In the U.S., it was Wernher von Braun, of course. In the Soviet Union, it was this man, Sergei Pavlovich Korolev. And he's sometimes called the mysterious chief designer. That was all he was known as. It was a state secret who this man was. And, in fact, if you mentioned his name, you were taken out into the birch forest and shot. And like Wernher von Braun, he experimented with rockets in the 20s and 30s as a young man, but he became a victim of the Stalin purges in the late 30s, and he was sent to a work camp. In this case, a particular kind of work camp called a Sharaska, which is maintained for scientists and engineers, and they were put into forced labor to help out during World War II. And of course, his job was to work on rockets for the World War II. And he emerged afterwards to investigate the Germans' rocket program. He was sent to Germany, brought back a bunch of V-2s and a bunch of German scientists. And then he personally led the Soviet Union into the age of ballistic missiles and rockets. His real interest, just like Werner's, was not so much military, but in fact to explore space. But he couldn't do the space exploration without the military's rockets and their money. And so to influence his government to conduct space exploration versus just building missiles, he engaged with this other man here, Mstislav Keldysh. And Keldysh was the head of the Soviet Academy of Sciences. And he became the face of the space program in the Soviet Union and was known generally as the chief theoretician. And there's no equivalent here in the U.S. To him. Now, Korolev is the designer of Russia's first ICBM. He started work on this in the early 50s. It was called the R-7. And it was required to carry this massive Soviet atomic warhead. It weighed about 5 times more than the U.S. equivalent for the same yield. They didn't have the technology that we had to miniaturize these warheads. And as a result, the first Soviet rockets were much more powerful than the U.S. rockets, much bigger. And therefore, actually a great boon eventually to space exploration payloads. The R-7 was first tested in April 1957, and Korolev actually had to fight the Army to use it during test flights to launch a satellite. We don't know what satellite that was. And he succeeded only when the development of the warheads ran behind the actual testing of the rocket. So he had extra rockets, and they just said, okay, why don't you just go ahead and launch your little satellite, kind of thing. Then, of course, we know that was Sputnik. And then later he had to develop a three-stage version called the Luna, which was used for the very earliest lunar missions in 1958-59. Then a four-stage version, later called the Molniya. It was developed for planetary missions and heavier lunar flights beginning in 1963. And in the 60s, the Russians controlled about 5 times more weight than the equivalent U.S. vehicle. The Molniya was 5 times more powerful than the Agena, which was used back then for U.S. missions. And the R-7, of course, became the basis for the most successful space launcher in history. It's now known today as the Soyuz, used for both manned and robotic launches. Of course, the world reaction to Sputnik took the Soviets completely by surprise. Khrushchev just thought this was some little sideline that Korolev had to do. Okay, you do your thing. And when they launched Sputnik, the world reaction just blew the Soviet leadership away. And they realized immediately the propaganda value of these civil space missions. And that opened the door to Korolev's requests to use the R-7 for Lunar and Planetary launch. And Khrushchev actually pushed him hard because he forced Korolev to rush to prepare a spacecraft in this three-stage rocket to beat the Americans' announced lunar launch, which was going to be in August of '58. And so what Korolev did, he put his first three-stage rocket on the pad, and he listened on the radio to see how the Americans were doing. He was ready to push the button if the U.S. launch succeeded. It didn't succeed, wiped his brow, took the rocket off the pad, and continued more testing. Now, it turns out that throughout the whole fall of '98, that the Russians and the U.S. traded 3 launch failures. These were Pioneers 1 through 3. And it was kind of a dramatic contest on both sides. The USSR was completely aware of what we were doing, day by day, hour by hour. But the U.S. was kind of groping blindly to try to seize the lead and had no information about what was going on in the Soviet Union, but Korolev prevailed. And the age of robotic, lunar, and planetary exploration actually began with the successful launch of Luna 1 on January 2nd, 1959, the first spacecraft to leave Earth orbit. It was the first lunar flyby, January 4th. Of course, it was designed to actually impact the moon, but it failed in doing that. The Russians, of course, never announced that. They just said it was supposed to be a flyby. Gee, it worked isn't that great. Then later, after another launch failure, Luna 2 became the first to impact the moon on September 14, 1959. Then Korolev built a much more capable spacecraft, with actually the very first 3-axis controlled spacecraft, Luna 3, and conducted a circumlunar flyby and took the first far-side pictures in October 7, 59. And of course, the U.S. was still trying to get its rockets to work at that time. Well, after the lunar successes, Khrushchev pushed Korolev for more. Korolev wanted to go to Venus, and he wanted to go to Mars. To do that, he needed a new 4-stage vehicle for the R-7. And he had to do all of this within 8 months, because Khrushchev says, I want this by the October Revolution, anniversary of the October Revolution. You got 8 minutes. And Khrushchev said something that was motivating. And it's actually amazing that Korolev actually got these things built in 8 months. A brand new 4-stage vehicle and a new spacecraft. The spacecraft was the first with solar panels to recharge the batteries because it was going a long distance. Onboard propulsion, first with onboard propulsion. It's underneath that dome that you see there. You can't see the nozzle, it's at the top of the dome. And long-range communications, first parabolic antenna, as you can see there. It carried a facsimile camera for flyby, infrared spectrometer, a UV spectrometer, all of which actually had to be removed in the end in order to save weight for diagnostic instruments that Korolev had to put on the brand new launch vehicle. So they only really carried space environment sensors. And the Venus one carried a small impact probe of this size that was designed to save the breakup of the spacecraft that nobody ever got there. The problem is that the first launch, is what you see here is the erection of the first Molniya on the pad. It carried a Mars spacecraft on top of it. It failed on October 10th, and the second attempt failed on October 14th. And then in February they tried 2 Venus launches. One of them was a success. And in fact, sent Panera 1 on its way towards Venus. But the spacecraft had a lot of problems. It had severe thermal and attitude control issues, and it failed 5 days later. But it's the first spacecraft ever successfully launched towards a planet. The 68 to 61 launches had been really rushed, only 8 months. And so Khrushchev took the next 2 years to improve his Molniya, give it more lift capacity, and develop a new generation spacecraft that was specifically designed for planetary missions. And all improved systems. It was a modular spacecraft. It had a cruise stage and a science compartment. And this kind of set the design standard for planetary spacecraft for the next decade in the Soviet Union. Here you can see it here. This is the cruise module. It contained all the avionics, navigation, and attitude control. This is the propulsion system. And below the waist here is the science compartment. In this case, this is a flyby module. Solar panels, hemispherical thermal radiators, a boom for the magnetometer, lots of antennas. So Mars 1, and the flyby module contained these same 3 instruments that were tried earlier: camera, 2 spectrometers. The entry probe module contained temperature measurements, pressure, chemical analyzer, gamma ray, surface analyzer, and a mercury motion detector. And the only one that succeeded its launch vehicle was Mars 1. It was the first spacecraft ever launched to Mars in 1962. And it suffered a lot of difficulties. It had attitude control problems and eventually was lost after about a flight of about 5 months. Well, after successes in impacting and imaging the moon, Korolev had stood down to develop these planetary spacecraft, and then he designed the new lunar spacecraft for a soft landing. And he based that new design on that 2MB planetary vehicle you just saw, with a cruise stage and a detachable lunar lander. The earlier Lunas flew these direct trajectories to the moon, Lunas 1 through 3. This one used the new 4-stage Molniya, and so what they did was just park it in Earth orbit with the 4th stage, and then at the right moment, just like we do now, ignite the 4th stage for a second time to send it on to planetary trajectory. It's a much more efficient way of doing things. And the lander carried only 2 instruments: a panoramic scanning spectrometer for imaging and a radiation detector. It had no solar panels, all battery. It was a 100-kilogram soft lander, and used airbags for terminal shock. Another country stole that idea many decades later. But boy, did they have problems with this. They had 11 failed missions over 2 years, 63 to 65. That's a record of failures that would have failed NASA. And in fact, JPL, if you remember, had like 6 or 7 failures in the Ranger program, and they almost lost their contract. The Soviet Union, 11 was not good. He got called in front of Khrushchev, and he got a finger wagged in his face, but he just kept trying. And that was a characteristic of the Russian program, that they just kept trying until they made it work. Luna 4 actually got launched to the moon, but its navigation failed and it missed the moon. Luna 5, its guidance failed during the terminal maneuver, it crashed. Luna 6, mid-course went awry, it missed the moon. Luna 7, it had attitude control problems and its retro system failed, it crashed. And Luna 8, when it approached the moon and they deployed the lander, the airbag was punctured and it crashed. But not a good record. Well, in addition to frustration at the moon, and during these years, the Soviets were again frustrated at Mars and Venus. The lessons from Mars 1 forced a complete redesign of the 2MB spacecraft, and became known as now the 3MB, the third Mars-Venus spacecraft. And the reliability of the 4th stage was increased. And to test all of these things, the new Molniya and the new spacecraft, they planned test flights. Which seems to be a good thing to do. But these just revealed more and more problems. So they tried a test flight November 11th of the Mars vehicle, just to send it. Mars wasn't there, but they were just going to send it to Mars distance to test it. That launch failed. And in February of '64, they tried a test launch to Venus distance. That also failed. But the problem was the Venus window was upon. And so they just went ahead and launched again, this time to Venus. Their first launch failed. The second one succeeded, but the spacecraft had problems. It developed a slow leak. Because remember, the spacecraft were pressurized compartments. They had so much mass they didn't have to worry about developing vacuum electronics. They just built a pressurized module, put vacuum tubes in. And they realized it was not going to fulfill its mission, so they named it Zond 1 instead of Venus 2 or something. Then later in the year, they tried a Mars flyby launch. It succeeded, but the spacecraft failed again after about 2 months due to multiple problems. And then they said, okay, we're having so many problems, we'll try another test launch. So in 1965, they tried a test launch to Mars once again, after working on the spacecraft and launch. Launch succeeded, and during the flyby of the moon, they wanted to test all the instruments out and how the spacecraft worked at the time. That all went just fine. And Zond 3 returned a lot of images of the far side of the moon. And it survived for 8 months, but it didn't quite make it to Mars distance. And then finally later on in the year 65, they tried 3 launches of Venus, 2 of which were successful, and Venus 2 and Venus 3 came that close to fulfilling their mission. The Venus probe, Panera 3, they both had thermal problems going inward towards the sun. And Venus 3 got to the planet in 17 days before it was to get there, simply due to thermal issues. Panera 2 actually made it to the planet and initiated its flyby sequence, and then was never heard from again. Tantalizingly close, frustrating losses, but encouraging enough to lead them to try new attempts in the next opportunity. Korolev's design bureau, which was called OKB-1, was responsible at this time for both human and robotic programs. He had the whole enchilada. He was almost like NASA. And by 1965, he was almost completely occupied with the human spaceflight program. And he had this long string of failures in the robotic program. And he realized that he just couldn't do both. And so he reluctantly transferred responsibility for the robotic Lunar and Planetary program to his good friend, Georgy Babakin's institute in Korolev, where it remains today. And he did that in kind of mid-1965. What Logic did was they took the year of 1965 to modify OKB-1's lunar spacecraft, and then on their very first try, early in 1966, after all those failures, they succeeded. And unfortunately, only days after Korolev's death. Korolev died in January 1966. And although they were lagging, the Soviets were lagging at Mars and Venus, they once again beat the U.S. to a space milestone. Lunar 9 was the first soft landing on the moon, and the first to return panoramic pictures from the surface. Surveyor 1 followed later in June '66, and Lunar 13 in December. Well, anxious to beat the Americans to lunar orbit, after having landed softly, the Americans had announced they were going to do this in mid-1966. So the Soviets quickly cobbled together an orbiter from the Lunar 9-13 vehicle. They used the cruise stage and then replaced the lander with a pressurized module containing readily available instruments that they could use. This was probably from a Cosmos Earth satellite series somewhere. And after one failure in March, they finally succeeded a month later with Luna 10. U.S. Lunar Orbiter 1 followed in August. So they did beat the U.S. to orbit, but the U.S. took the first lunar images in orbit. And this was the first evidence that the U.S. was beginning to catch up. The U.S. finally succeeded with the first milestone. Korolev built an improved series beginning with Luna 11. These were to be imagers. The imager failed on Luna 11, but it did succeed on Luna 12, and that series was quite successful actually in mapping the lunar environment and obtaining data for the manned space program. The real purpose of this series, Luna 11 through 14, was to map the lunar gravity, because they ran from 10 and it was very, very rugged. They had trouble navigating with the orbit. They actually were the first to detect mass cones. They lost credit for it because they didn't publish it. The U.S. got credit for that. They did radiation and magnetic field mapping. They looked for cosmonaut landing sites with imagery, and they did a lot of technology tests for the piloted program. They were testing lubricants for vacuum use in space and those such things. Well, during the same time period as these new lunar successes were occurring, Lavochkin made significant improvement to Korolev's 3MV planetary spacecraft as well, and they beefed up the probe to handle a Venus pressure of 18 atmospheres and about 400 degrees C, because some of the data from Mariner 2 and the ground-based experiments were beginning to show that Venus probably had a hot surface, but it was controversial still. But the good thing is that they were awarded once again, immediately with a success, and Panera 4 became the first spacecraft that penetrated the Venusian atmosphere. You can see the spacecraft here is again the same 3MV design. You can see here's the avionic sensors on the back here, and the parabolic antenna, solar panels, propulsion system up here. This is the cruise stage, and this is the probe. Here's the probe with its ablation, one of the top half of the ablation field removed, and this is the parachute cover. It's ejected, and this is the probe that's contained inside, including the radio altimeter here. But the controversy, its last measured temperature was 262 degrees C. It's sometime later, as the commutator moved around to the next instrument, the last pressure measured was 18 bar, which was its design limit. And there was some confusion at the time as to whether or not it actually hit the surface. The altimeter actually did not work properly. It seemed to indicate that they had been at the surface. And there was a conflicting interpretation of these terrestrial data and the Mariner 2 data on Venus. It wasn't settled yet. Finally reconciled by Mariner 5 in 1967. But this controversy was not settled in time for the next Panera series, 5 and 6. But in any case, they did manage to strengthen the probe to about 25 bars, and they used smaller chutes to get the spacecraft to the ground quicker before the temperature got too high. Panera 5 and 6 were both successful, but they also imploded at their design limit, about 25 bars, 27 bars. And here's the data that they received. The surprise was that the Venus atmosphere did not have a lot of nitrogen. It was not thought it was almost entirely CO2. And so little oxygen in water. And these were temperatures derived at the surface by using an atmospheric model from Mariner 5 and the Panera 5 and 6 data. Well, in 1966, I can ratchet back a little bit here, Lavochkin, we're going back to Mars here again. Lavochkin decided to abandon this 3MV vehicle for Mars because it had so many failures, and not one of them had even come close to meeting its objectives as opposed to the Venus. And so they opted to go for a new and heavy spacecraft in the 5-ton weight class, metric ton, launched by this new Proton vehicle. Wouldn't you like to have 5 metric tons on there? And this is in the mid-60s. Launched by this new Proton vehicle. And Mariner 4 had also shown the atmosphere of Mars to be very, very thin, which was a surprise. And that required a whole new type of lander than the one they were trying to use. The one they were trying to use would have totally failed. So what they did was they sat down and they devised a whole new comprehensive plan for both Mars and Venus. And the goal was soft landing. Remember, the U.S. was just doing flybys back in those days. And so they defined a 1969 campaign to get data on the atmosphere that they needed to design this new lander, and to get the ephemeris data on Mars so they could actually target the lander properly. And this whole program was also designed to upstage the Mariner 69 flyby by doing a probe, and upstage the Nut 71 orbiters by doing a lander. And this was a brand new heavy design for Proton. It was a three-year development challenge. 3 years is kind of standard for us, if you remember. Actually, sometimes a bit of a challenge for us even. And all of this was still, a lot of the attention of the engineers was diverted by this rush to succeed at Venus as well in 67. And the first they tried to design a spacecraft based on a lunar design they had. The man program had been designing a robotic lunar spacecraft to land a rover for cosmonaut purposes. I'll get to that in a minute. They tried modifying that spacecraft for Mars. And after a year and a half, they decided that was just not going to work. They just couldn't do that. They needed a different design for Mars. And so with 13 months left to go, they totally redesigned the entire spacecraft. And ended up, with a 3,500 kilogram orbiter and almost a 300 kilogram probe. The probe was to be deployed from orbit, and unfortunately, since they had so little time, they had a lot of mass problems, they had a lot of testing time problems, and so they just deleted the probe and bolted on some orbiter instruments. Of course, the problem is that both protons exploded. In March 27th of 69, the third stage exploded shortly after ignition, and the second try, the booster, exploded. Now, the U.S. had been tracking a Russian spacecraft since the 60s, and generally could tell where these things were going after launch, because they could track them. These they weren't able to track because they were lost so early in their flights, and so the purpose of these launches went unknown. So they didn't have a clue that they were actually trying to go to Mars back then. With such a capable mission, it would have scared us to death, given what it is that we were trying to do, just a little flyby. Well, in fact, the launch failure probably saved the Russians an embarrassment, because the spacecraft had been so rushed, it would have had many problems. Well, I mentioned the cosmonaut program and the rovers, and in 69, late 68, early 69, while the U.S. closed in on a manned landing on the moon, the Soviet Union decided to counter with robotic missions because they pretty soon realized that they were way too far behind. And they had in development this new Proton-launched heavy lunar spacecraft designed to land a large rover. And the purpose of that rover was to actually go first before the cosmonauts, scout out the site, act as a beacon to guide the landing for the cosmonauts, and to provide safe conduct to an earlier spacecraft that had been landed robotically as an escape vehicle in case something happened to the vehicle that the cosmonaut landed. And so what Lovikin did was to adapt this design for robotic missions. It was especially constructed around 4 large propellant tanks, see these right here, conducted by cylindrical sections. It had a lander here with egress ramps for the rover, and the rover sitting on top of it. It had these backpacks, these detachable backpacks to carry propellant and batteries and avionics, and this was to be jettisoned in lunar orbit after its final orbit before landing. And in an effort to upstage the U.S. Apollo 11, they rapidly modified this for a sample return. They added an avionics ring for the sample device. This is the sampler. And then they added the sample return stage. They designed a very ingenious return trajectory for specific landing sites on the surface that, with proper timing, eliminated completely the need for any complex return navigation or any need for mid-course corrections at all. You launch it at the right time, it landed on the Earth in conjunction. Very clever. The Soviets were very, very clever with navigation. Very, very innovative. Well, work began on this sample return modification late in 1968. And it's just amazing that such a complex spacecraft could be so readily modified in so incredibly short a time. And it actually flew after the first rover attempt failed in February of 69. All of this is a testament to Russian culture. Their attitude was, just do it. Dismiss the hardships. Forget about that stuff. Use whatever you have on hand, fix it on the fly while you're building and after the build. Order a rocket from the Army, erect it, bolt your spacecraft on, and light the fuse. That's the way they worked. And their rockets were readily at hand. The Samara factory was turning out R7s, Ford assembly line production fashion. If that one rolled off the line and it didn't have a mission, they just stacked it up like cordwood. Call it the Army, you got one. Very different than today. Well, after one launch failure in June of 15, a month before the Apollo launch, Lunar 15 reached lunar orbit before Apollo 11 got there, and it failed on July 13th in attempting to land while the Apollo astronauts were still on the surface. And sample return and lunar sample return, lunar rovers, are robotic achievements that have never been equaled by the U.S. The rovers were loaded with instrumentation. They included a whole set of panoramic cameras to get the complete 180-degree vertical view around the rover. This is a picture from the vertical one, and these are segments taken from the horizontal 360-degree horizontal panoramic view that they would get. And they also had two stereo pair cameras that were about human height on the front to help the drivers. You can see here, this is Lunar 2, and this is a picture it took of its lander. And here's a recent picture from a lunar reconnaissance orbiter. You can kind of see the ramp here and the tracks of the rover. And this picture was taken from this station right here. Both rovers were superb achievements. Lunar Cod 1 traveled over 10.5 kilometers in 10 months. Lunar Cod 2 traveled 37 kilometers in 4 months. Both were spectacular successes, and they turned a whole lot of data on the lunar surface environment, the soil composition and mechanics, dust, magnetic field, and local geology. The sample return missions were successful too. They had a few more failures of these, but they had a number of successes as well. And in 1970, on the 24th of September, Lunar 16 became the first successful robotic sample return mission from the moon. It returned 101 grams of the sample core. Excuse me. This is a diagram of the vehicle. This is the deployed. This is the arm for the sampler. This is deployed on the surface, and there's a drill in here. It's got a drill core, and it would swing back up, turn around a little bit, and put the sample inside a little door here. Door would close, and then at the right moment, they would launch this bit back to the Earth. And here's a picture of the first return core right here. And again, this is a picture from LRO. Lunar 16 sitting on the surface here. 1971, they did it again. They tried Lunar 18, and it ran out of fuel at just about 100 meters altitude, and then it crashed. Somebody had forgotten to fill the tanks. In 1972, Lunar 20 succeeded. It returned 55 grams. Trouble with this drill. In 1974, Lunar 23 landed very hard and damaged its sampler, and so no return was attempted. And finally, in 1976, Lunar 24, with an improved drill, returned about 170 grams. And with Lunar 24, 1976, Soviet exploration of the moon ended. After success with the Lunar 16 sample return and Lunar 17 rover, the Soviets once again modified this basic spacecraft and replaced the top portion of it with an orbiting compartment. And the objectives were tied to the lunar cosmonaut program at the time. The goals for these were to obtain surface imaging at very high resolution, 100 meter by 400 meter pixels, to obtain altimetry measurements of the lunar topography for cosmonaut landing sites, to do remote surface composition and dielectric properties of the surface, and to map the lunar gravity field even more accurately, and to get radiation meter, micrometeorite plasma data on the environment of lunar orbit. Both were successful, but there were very few results ever published, and I think that's because of its tie to the cosmonaut program. And we all know that eventually the Soviet program to land cosmonauts on the moon was finally terminated in the mid-1970s. Well, back to Venus now. So after 11 attempts in almost 10 years, they finally achieved success at Venus with the Venera 7. The Venera 7 capsule had been beefed up once they knew about the surface conditions, but they beefed up the Venera 7 capsule to handle 180 atmospheres of pressure. They really made sure that this was going to last, and 540 C for 90 minutes. And that takes mass. And so to do that, they had to sacrifice most of the payload. There was only a pressure sensor and a temperature sensor, the altimeter, and a simple gamma ray spectrometer on board. Of course, you get the Doppler winds for free, just because of the radio. And they used a much smaller chute, kept cutting down the size of the chute, much smaller chute to get to the surface as quick as possible and maximize their time on the surface. And what happened, though, is the parachute ripped. And then it failed after a while and dropped the capsule. And the capsule hit very, very hard, and the signal all but disappeared at impact. But what was interesting is, here's, of course, is the spacecraft, and this is the landing capsule. And you can see that this is from the data. You can see here the parachute was deployed right about here, and right about here they unreef it. It was a reefed parachute. It drops a bit faster. And then the parachute ripped right here, and this big stream parachute behind the vehicle, and it went into what's called a swoop and glide set of oscillations. And then right here the parachute failed, and it pre-fell to the surface, hit the surface, and then there's all the static. Well, one engineer spent his holidays, his Christmas and New Year's holidays, looking at the data, and he found, well, you know, there's a little signal in here. And sure enough, there was about 23 minutes worth of signal there from the surface. Apparently, the lander had bounced and had tilted over, so the antenna was not pointing to the Earth, but they did get enough signal to get some data back. The other unfortunate thing is that the instrument commutator had failed, and so they only got temperature data along with the Doppler. And so the next opportunity, that they sent Panera 8, this time to the day side. All these missions, Venus has been sent to the dark side because that's the easiest thing to do. But they had ideas of sending a much more capable lander, and they needed information on the surface illumination to see if they could take pictures from the surface. And so they sent Venera 8 to the twilight side to get data on the visibility of the surface. And now they knew what the surface was like. They backed off and designed it for 105 bars. They added a lot more instruments, and a deployable antenna could throw off the top of the capsule and make sure that they got the data. And it was a complete success. They got profiles of temperature and pressure and wind. They got solar flux from one altitude all the way to the surface. They identified 3 different cloud layers in the upper atmosphere of Venus. They measured its atmosphere composition to much better precision. And they measured 93 bars and 470 degrees C at the surface. And they got some gamma ray surface composition. Okay, now we're going to hop back to Mars again, because that's the way they kind of do things. The opportunities come along, and you go where you can. So for 1971, the Soviets completely trashed their Mars 69 design. Now they had some time. They could take the time to design a proper spacecraft. So this complete redesign ended up being like a 3,440 kilogram orbiter with a 1,210 kilogram entry vehicle. I'm loving these numbers here. And 360 kilogram lander. And the problem was they had failed to get the atmosphere data they need to design this thing in '69. They had failed to get the ephemeris data. But what they did find to do is they just read the literature on Manner 6 and 7. And that's how they got their atmospheric data. And then all this was published. It was enough for them to design this EDL system. But the U.S., this was in the bad old days, this was in the Brezhnev days, the U.S. would not release the ephemeris. That was engineering data. So the U.S. just can't have it. And so they decided early on to send an early orbiter before the landing spacecraft. And the orbiter would get there, get into orbit, and it would act as a beacon to help guide the later spacecraft which were launched to target the landers. Well, they knew they'd had problems with Mars spacecraft in the past, so they had a backup system. And it was a very clever, but also very risky system. It required on-board automatic optical navigation, where the spacecraft, without any help from the controllers, would sense where the planet was, do its optical navigation. The computer would then design the mid-course maneuver a few days out from Mars and do the correction. And it's a good thing because that Pathfinder orbiter launch was a failure. And almost miraculously, this optical navigation scheme really worked, almost perfectly. The U.S. didn't do anything like this for decades. And of course, this was all done without our knowing how these things were accomplished. This is the spacecraft here. They're all designed around the propulsion system. These are the propulsion tanks, and the propulsion engine is underneath this toroid. It's at the bottom here. Here's the nozzle and the toroid. This is an avionics toroid. It contained all the instruments. These are optical navigation sensors, solar panels. This is the parabolic antenna. This is the lander on top, the EDO system. This is what it looked like. It's the familiar open cone, but they had no back shell. They just had these struts that kind of tied everything together. This is solar panels. This is the lander right here at the bottom. This is another toroidal instrument container, also contained a parachute. And this is the propulsion system. This guy actually had a propulsion system on it. And this is the lander, two panoramic cameras. It had it's not shown here, but it also had a little tiny rover and a whole set of instruments. There were 13 instruments on the orbiter. 8 on the lander. There were 2 panoramic cameras. There was accelerometers, pressure, temperature, wind, X-ray spectrometer, this little 4.5 kilogram walking rover called a Mars Republic. And here's how it worked. This shows the EDL sequence for the 1971 and also the 73 missions. They worked exactly the same way. The orbiter was actually targeted for the orbit insertion point. And because of that, the EDL system had to have a propulsion system on board so it could retarget itself for the entry corridor. The EDL package was deployed at about -6 hours, about 6 hours before MOI. The spacecraft essentially turned to the right attitude, released the EDL system, and then the solid rocket fired on this EDL system to target the entry point. The propulsion system was then ejected, and the spacecraft reoriented itself to entry attitude, and spun up for stability control. And then after peak acceleration during the entry, it was spun down because you no longer needed to spin for stabilization at that point. And then the descent sequence was triggered after reaching Mach 3.5, and it used a series of 3 chutes: a pilot chute, a drogue chute, and then a reefed main chute. And here's the reefed main right here after that was all done. Then the lander was exposed by dropping the aeroshell. The main parachute was unreefed and exposed the retro system. The retros were fired, and the lander was dropped at about 20 meters altitude for about 10 meters per second impact velocity. The whole thing was amazing because, in fact, this whole optical navigation system scheme worked perfectly for both Mars 2 and 3. Controllers had nothing to do with it. Mars 2 was unfortunately improperly targeted by the computer. And there's a story about that, but I don't have time. And was put on a too steep entry path and crashed. But Mars 3 worked just fine. It went through this whole EDO sequence. It landed successfully. And as designed, it turned on its transmitter 90 seconds after landing and transmitted to the incoming spacecraft prior to MOI. but only 20 seconds of data after which the signal died. It only got 20 seconds of really what's mostly all noise. The orbiters had telemetry, they had telemetry problems, they had camera problems, they had this big dust storm at the time, and there very little data came from Mars 2, and only about 60 images from Mars 3, and most of those were useless because they were mostly of dust. But they did get data on the atmosphere, surface properties, gravity, and the orbital environment. And then in 1973, this poor doomed Mars fleet, because the Soviets were aware of U.S. plans for Viking, and that the lander was more sophisticated than theirs, and they were chagrined by Mariner 9's success at the same time that they had so little success in 71. They were just simply determined to beat the U.S. to the surface in 73. And this was a period of time, so there was a data exchange, and they got the ephemeris they needed. But this 73 fleet was doomed to a real fatal error. They were essentially identical spacecraft to the 71, almost virtual copies. But the engineers substituted a new aluminum lead transistor for the old gold lead transistor, and only discovered a few months before launch that it had a short lifetime to failure. And in fact, there was a 50% calculated chance of failure during the flight time of these spacecraft. And this would have dictated postponement reviews. And the engineers argued heavily for delay. But in this rush to beat the U.S. to the surface, the decision makers insisted on the go-ahead, and that turned out to be a disaster. And in 1973, they could not fly orbiter-lander combinations. They had to fly, if they're going to have a lander, they had to do it from a flyby, not from an orbiter. And so they had to send 4 spacecraft, 2 orbiters, 2 flyby landers, and they all suffered tragedies. Mariner 4 had computer problems. It couldn't make its second mid-course. The engine failed to fire for orbit insertion, and it simply flew past the time. It took a few pictures, but that was it. Mars 5, the other orbiter, it actually achieved orbit, but at orbit insertion, something happened and it triggered a leak. And so we had a pressurization failure, and the spacecraft died after 14 days, and just simply no results. So now there was no orbiter around the planet to relay data from the landers that were coming in. Fortunately, they did design a new radio system, separate radio system, where the flyby spacecraft would get data from the lander just after landing. And that system worked. Mars 6, it conducted to begin this just amazing flight. After its first mid-course, it suffered failures like every one of these things did, and the downlink failed. The Russians had no idea if the spacecraft was still there, still working, and so they just sent commands to it in the blind, hoping it was still there, hoping it was still working. This spacecraft did its navigation automatically. It did its second mid-course all by itself. Soviets knew nothing about it. They couldn't know anything about it, no downlink. And then it made its third mid-course correction using the optical navigation system at Mars, all by itself. And the first time that the Russians knew that Mars 6 was a success, when they started getting transmissions back from the probe on descent. And so the descent sequence worked. This is just a monumental achievement on autonomy. It's just amazing. But the lander, they lost signal from the lander just as it was released. And it was released at a fairly high velocity, so it's probably no surprise. Mars 7, its entry system simply didn't fire the retro, and it missed the pilot. And they did get some descent data from Mars 6. The transmission was garbled because of the problems with this transistor, and some temperature, some pressure data, but nothing very much. Mars 5, they got some data on orbital environment and some imagery from 4 and 5, but there was very little result from a huge, massive investment. It's really a shame. And you know what, I've gone through about 50 minutes here, and I've only gotten to 1975. But I have to tell you that the first part of the Soviet enterprise was probably the most dramatic and the most interesting. I think I should probably stop here. And the rest of the story is simply they had a great success at Venus, beginning with their Paneras 9 and 10. They had great success later with the Vega spacecraft, which went to Venus, dropped the balloon, dropped the lander. It went on to Halley. It was a huge international success. They had an open call for instruments on this spacecraft. It was highly unprecedented in this closed society. It was a preview of perestroika. And they became the leaders in the 80s for international robotic planetary exploration. Because they had these big, heavy spacecraft. They could offer hundreds of kilograms of space for people who wanted to fly instruments on them. And they flew with Christmas trees, 13, 14, 15 instruments. These were massive spacecraft, 5 and 6 metric tons. The U.S. couldn't compete with them. Just simply could not compete. The problem was is it all came a cropper later in 1989 with Phobos, another international call, big international cooperation, this time even with Western Instruments Award. And both these two missions, Phobos 1 and 2, failed. Phobos 2 had the planet before it got its Phobos. And so while in the 1980s the Russians demonstrated how to do an international flight program, it also demonstrated how debilitating these losses could be to the international community if they didn't work. Then there's the Mars 96 story, which I think most of you know. Another disaster for the Russians. But all in all, their program was very exciting. It was very bold, far bolder than the U.S. was. The U.S. was much more conservative, did things step by step by step. And the Russians, partly in order to try to beat the U.S. and demonstrate their own technical prowess, tripped over themselves quite a lot beginning in the late 1980s. But that's another story. Thanks for listening.